Hello, everyone. Imagine a world where a life-changing prosthetic hand doesn't cost a fortune. Here at Kai Robotics, we've made that vision a reality. Introducing our low-cost, innovative prosthetic hand designed with cutting-edge technology, 3D printing, and powered by simplicity. It's durable, functional, and made for everyone. And here at Kai Robotics, we are empowering lives one hand at a time.
Millions of people around the world face mobility challenges due to limb loss. Advanced prosthetic options exist, but their high costs make them inaccessible for many, especially in low-income regions. Our solution? A 3D printed myosensor-enabled prosthetic hand that is both affordable and highly functional. By leveraging low-cost materials and innovative design, we aim to make advanced prosthetics accessible to all. Restoring mobility, improving lives. Together, we're making affordable prosthetics a reality.
KI Robotics, redefining possibilities, empowering lives through intelligent prosthetics and automation.
Prosthetics are commonly used by people who have lost limbs or were born without them, often due to medical conditions such as diabetes, cancer, or infections, trauma such as accidents, injuries in war or natural disasters, cognitive conditions such as birth defects or developmental issues, rehabilitation purposes for temporary prosthetics during recovery, and as well as animal prosthetics are also developed to improve their quality of life, especially for pets, farm animals, and some wildlife. Losing a limb is a challenge faced by millions across the world, but what causes it? Let's break it down. Over half of all amputations, around 54 to 60%, are due to vascular diseases like diabetes and peripheral artery disease. Poor blood circulation leads to infection, tissue damage, and ultimately amputation. Next, trauma accounts for 30 to 35% of amputations. Accidents, workplace injuries, and even war wounds are common culprits, especially in younger populations or areas affected by conflict. A smaller percentage, about 2 to 4%, results from aggressive cancers like bone or soft tissue sarcomas. Finally, congenital conditions account for 1 to 2% of cases. These often take place at birth, with children requiring prosthetics tailored for their growth and unique needs. Understanding the causes of limb loss help us focus on prevention, care, and innovative solutions. That's why we invented BioFlex, featuring a low-cost design. Affordable, practical prosthetic solutions can be provided for a fraction of the cost. Let's take a look at the assembly. In this section, we will talk about the bill of materials, the schematics, the code, and finally we will give a short video demonstration of the working product. Looking at the bill of materials, we can see that we have a MyUwear muscle sensor, the reference cable, disposable service electrodes, a micro servo motor kit that comes in a 5-pack, a microcontroller nanoboard, multicolored wires, 3D printed parts that only amount to $107 US. Looking at these schematics, we can see the layout of both the servos and the MyUwear muscle sensor hooked up to the Arduino Nano. The MyUwear muscle sensor has a positive, a negative, and analog output. The servos have a positive, a negative, and a signal that go into a digital pin. The MyoWare muscle sensor works using electromyography or EMG. Muscles generate tiny electrical signals when they contract. These signals are caused by activation of motor units in the response to signals from the nervous system. The MyoWare sensor outputs an analog voltage signal that corresponds to the muscle activity. The Arduino reads the sensor's analog output using the analog read function. This provides a numerical value typically between 0 and 1023 on the 10-bit ADC that corresponds to the strength of the muscle signal. Utilizing the servo library in Arduino IDE, we can clearly define the pins of the servos, the analog pin for the Myo sensor, and then using the Myo sensor value in the analog read function, we can set a threshold of when the reading reaches above 790 to trigger the servos. So here we can see a completely 3D printed and assembled prosthetic right hand. It is powered by 5 servos, connected to digital pins D4, D5, as well as D9 to D11 on the Arduino Nano. Fishing wires are used to resemble the flexion in the fingers. Looking at our Arduino Nano, we can see that we are using digital pins D4, D5, as well as D9 to D11. We're using one analog pin, A0, and also we added a negative terminal connection to the Arduino Nano because we were facing issues with power interference from the PC since we're not using a USB isolator, which seemed to straighten out the readings we were getting from the Myo sensor. So looking at pin A0, we could see how the MyoWare 2.0 sensor is connected to the Arduino Nano. And this analog pin is the data input for the Arduino Nano to translate into servo positions depending on the electromyography readings from the muscle group itself. Here we could see the MyoWare 2.0 muscle sensor. This is just a shield to protect the delicate components on top of the circuit board. We could see that it also utilizes 4 biometric gel pads. These gel pads are what's used to connect the device to the muscle group on the forearm. Here we could see that we have a reference cable to be placed away from the muscle group to act as a reference, to compare the new readings of the muscle group to a position that is free of electromyography readings. This comparison is used to translate into servo positioning that will then flex or extend the fingers on the prosthetic hand. Lastly, it's important to look into the power supply powering this system. Here we have it set at 5 volts. Running away from the power supply, we have an extension cable that splits into positive and negative currents running to the servos. We have a positive and negative cable running to the MyoWare sensor. And then lastly, we have a negative cable running to the Arduino Nano. So here we could see the MyoWare sensor hooked up to my forearm on the main muscle group, as well as the reference cable away from this main muscle group. In terms of flexion, the MyoWare sensor will pick up the Myo electric reading, compare it with the reference cable, and then process it for servo positioning. Here we could see it hooked up and powered. In 2023, the global human prosthetics market was valued at $7.5 billion US, projected to grow at a 6% CAGR, reaching $11.3 billion by 2030. Adding 75 million for animal prosthetics, which is also expected to double, the combined market will approach approximately $11.5 billion. Currently, myoelectric prosthetics make up just 16 to 20% of the market, leaving nearly 9 to almost $10 billion in untapped potential by 2030. With diabetes-related amputations expected to rise, already causing 1 million amputations globally per year, demand for innovative smart prosthetics is set to soar, creating an unparalleled growth opportunity. Marketing costs could include $0.50 to $3 per click for digital ads targeting amputees and healthcare audiences. Partnering with nonprofits for additional assistance may add 1 to 10% to product costs. However, they do come with minimal upfront expenses. Local campaigns in amputee communities could add another 20 to 35% of product costs if it is not covered by any external fundings such as external organizations or governments. However, these methods will ensure targeted outreach and global engagement. AI can be used to smooth out sensor readings, learning from datasets for universal sensor placement. As 3D printing advances and costs decrease, it will further lower production costs and expenses. Additionally, feedback sensors can mimic pressure and heat, providing users with a sense of touch in the prosthetic itself and enhancing the prosthetic experience.